318 pounds. That's what separated genius from madness in 1961. That's less than two full-size men, about the weight of a motorcycle engine. And it was going to either revolutionize the automotive industry or destroy General Motors' reputation for engineering. This chunk of aluminum sitting in Buick's Flint, Michigan facility wasn't just an engine. It was a 318-pound middle finger to everything Detroit thought it knew about building V8s. Picture this. It's January 1961, and you're standing in a Buick dealership. The salesman is trying to tell you about this new special model with its revolutionary aluminum V8. You pop the hood, expecting to see another massive iron block like every other American car. Instead, there's this compact, almost delicate-looking engine that seems like it belongs in a European sports car, not an American family sedan. The guy next to you laughs and says it looks like a toy. 5 years later, that same toy would be powering Range Rovers through the Sahara Desert. 40 years after that, it would still be in production, having outlived every single iron V8 from that era. This is the story of the Buick 215 V8. The engine that was too advanced for its own good failed spectacularly in America, and then conquered the world from the most unlikely place imaginable, a British factory that had never built an aluminum V8 before. To understand why General Motors would risk everything on an aluminum engine in 1961, we need to travel back to the late 1950s when the American automotive landscape was changing faster than anyone predicted. The Big Three had just witnessed something that shook them to their core. The Volkswagen Beetle was selling 150,000 units a year in America. The Nash Rambler was stealing customers who wanted smaller, more efficient cars. Even more terrifying, rumors were swirling that Ford was developing something called the Falcon, a compact car that would launch in 1960. GM's response came in 1959 when Ed Cole, Chevrolet's general manager, convinced the corporation to develop 3 compact cars simultaneously, one each for Buick, Oldsmobile, and Pontiac. But here's where it gets interesting. While Chevrolet was developing the Corvair with its air-cooled rear engine, the other 3 divisions wanted something more conventional. They needed a small V8 that could fit in a compact car, deliver decent fuel economy, and still provide that V8 character Americans demanded. The traditional approach would have been to simply shrink an existing iron block design. Take the 283 small block, reduce the bore and stroke, call it a day. But Joe Turley, Buick's chief engine designer, had been experimenting with aluminum casting techniques since 1956. He'd seen what Reynolds Metals Company was doing with their new permanent mold casting process. He'd studied the aluminum engines Rover was attempting in England, though those were failing miserably. He believed aluminum was the future, the development. Team faced a seemingly impossible challenge. The engine needed to weigh less than 350 pounds, complete with all accessories. It had to produce at least 150 horsepower to move a 2,500-pound car acceptably. It needed to cost less than $200 per unit to manufacture, which in today's money is about $2,000. And here's the kicker. It had to be ready for the 1961 model year, giving them less than 24 months from concept to production. The engineering started with the block. Using Reynolds Aluminum's new 356 T6 alloy, the team created a block that weighed just 41 pounds bare. The comparable iron 283 block weighed 125 pounds. The casting process was revolutionary for mass production, permanent mold casting instead of sand casting, which gave them dimensional tolerances of plus or minus 0.02 inches. That's about half the thickness of a human hair. But aluminum presented massive challenges. Its thermal expansion rate was twice that of iron. At operating temperature, an aluminum engine grows significantly more than an iron engine. This meant every tolerance, every gasket surface, every bearing clearance had to be calculated for both cold and hot conditions. The engineers discovered that traditional head gaskets would fail within 5,000 miles due to the aluminum's expansion and contraction cycles. Their solution was ingenious. They developed a special sandwich-style head gasket with a steel core and copper facing that could handle the thermal cycling. They also spec'd nodular iron valve seat inserts that were pressed into the aluminum heads with an interference fit calculated to maintain proper retention at all temperature ranges. The sodium-filled exhaust valves were a necessity, not a luxury. Aluminum conducts heat 3 times better than iron, meaning the heads would literally melt without advanced heat management. The cylinder heads themselves were works of art. Each one weighed 21 pounds compared to 44 pounds for an iron small block head. The wedge-shaped combustion chambers were designed for a compression ratio of 8.8.1 on the base engine, allowing it to run on regular fuel despite the aluminum's superior heat dissipation properties. The high compression variant ran 10.25.1 and required premium fuel but produced 185 horsepower in Buick trim. Here's where the technical specifications become truly impressive. The bore was 3.5 inches with a stroke of 2.8 inches, giving exactly 215.5 cubic inches of displacement. That short stroke meant the engine could rev to 5,500 RPM reliably, unusual for American V8s of the era. The connecting rods were forged steel, necessarily beefy to handle the stresses in the aluminum block. The crankshaft was cast iron rather than forged steel to save weight and cost, balanced to extremely tight tolerances to prevent vibrations that could fatigue the softer aluminum. The intake manifold was another aluminum casting, weighing just 8 pounds versus 25 for iron. Buick used a 2-barrel Rochester carburetor for the base engine, while the Power Pack version got a 4-barrel. The entire induction system was designed for velocity rather than volume, small ports that kept the airspeed high for better fuel atomization and low-end torque. Now here's what made engineers' jaws drop. The complete engine, ready to run with all accessories, weighed between 318 and 324 pounds depending on configuration. A Chevrolet 283 small block weighed 475 pounds. The Ford 289 tipped the scales at 460 pounds. Even the compact Ford Falcon's 144 cubic inch 6-cylinder weighed more than the Buick 215 V8. The first prototype engines were running by March 1960. Initial dyno testing revealed a problem nobody anticipated: the engine was too smooth. The aluminum block damped vibration so effectively that engineers couldn't feel when the engine was running at idle. They had to add a slight imbalance to the accessories drive to give drivers tactile feedback that the engine was actually running. Durability testing was brutal. Engines ran wide-open throttle for 500 hours straight. They endured 5,000 thermal cycles from 40 to 250 degrees Fahrenheit. They were subjected to 50,000 miles of accelerated corrosion testing with saltwater spray. The aluminum showed a disturbing tendency to corrode when exposed to certain coolant additives, forcing GM to develop a special antifreeze formula just for these engines. The manufacturing process was unlike anything Detroit had done before. The Flint engine plant had to be completely retooled. New furnaces for melting aluminum, new permanent mold casting machines from Denmark, new machining centers that could handle aluminum's different cutting characteristics. The total investment was $75 million in 1960 dollars, nearly $1 billion in today's money. Workers had to be retrained. Aluminum requires different cutting speeds, different tooling, different handling. Drop an iron block and you might crack the floor. Drop an aluminum block and you've scrapped a $50 part. The quality control was extraordinary. Every single block was pressure tested, X-rayed for porosity, and dimensionally checked on a coordinate measuring machine. The base 215 in the Buick Special produced 155 horsepower at 4,600 RPM and 220 lb-ft of torque at 2,400 RPM. Those numbers might seem modest, but remember, this engine weighed 150 pounds less than any competitor. The power-to-weight ratio was revolutionary. In the Oldsmobile F85 with the 4-barrel carburetor, it made 185 horsepower. Pontiac's version in the Tempest was detuned to 155 to protect their larger engine sails, but Oldsmobile wasn't satisfied. They wanted more. In April 1962, they introduced the Jetfire, the world's first production turbocharged car. The Garrett I-Research turbocharger, roughly the size of a cantaloupe, boosted the 215 to 215 horsepower, 1 horsepower per cubic inch, the holy grail of naturally aspirated performance. The turbo system was complex, featuring a fluid injection system that sprayed a water-methanol mixture to prevent detonation. It was too complex for 1962 technology, and most owners had reliability issues. Track testing revealed the 215's true advantage. In a 2,500-pound Buick Special, the aluminum V8 gave a front-rear weight distribution of 53/47, nearly perfect. The same car with an iron V8 would have been 57/43, causing understeer and poor handling. The reduced weight over the front wheels meant better braking, sharper turn-in, less tire wear. The automotive press was divided. Car and driver called it the most sophisticated engine in American production. Motor Trend was skeptical, questioning long-term durability. Hot Rod magazine saw the potential immediately. Here was a V8 that could be swapped into sports cars, giving V8 power without V8 weight penalty. Sales started strong. 1961 saw 67,000 Buick Specials sold with the 215. Oldsmobile moved 42,000 F85s. But problems emerged quickly. Dealers weren't trained on aluminum engine service. Mechanics would over-torque head bolts and crack the aluminum. They'd use the wrong coolant and cause corrosion. They'd mistake the engine's smooth running for a problem and try to fix it. The corrosion issue was the killer. Despite GM's special coolant, owners would top off with regular antifreeze. The dissimilar metals, steel bolts and aluminum blocks, created galvanic corrosion. Engines that should have lasted 100,000 miles were failing at 30,000. Warranty claims skyrocketed. GM's reputation for bulletproof reliability was taking a hit. By 1963, the decision was made. The 215 would be discontinued after the 1963 model year. The tooling was expensive, the warranty claims were mounting, and new thin-wall iron casting techniques were making lighter iron blocks possible. The 300 cubic inch Buick V8 that replaced it weighed 100 pounds more but cost half as much to manufacture and had zero corrosion issues. Total production was just 376,114 engines over 3 years. In Detroit terms, that was a failure. The tooling alone cost $200 per engine to amortize over such a small production run. GM was eager to cut their losses. Enter Harry Webster, chief engineer at Rover in England. Rover had been struggling with their own aluminum V8 design, a 2.5-liter unit that was overweight, underpowered, and unreliable. Webster flew to Detroit in 1964 to study the 215. He was stunned. Here was exactly what Rover needed: a lightweight, compact V8 perfect for their luxury saloons and the newly conceived Range Rover. The negotiation was swift. GM wanted out. Rover wanted in. For $750,000, Rover purchased all the tooling, blueprints, and manufacturing rights. GM thought they were dumping a failed experiment. Rover knew they were buying the future. But Rover didn't just copy the 215. They improved it. British Leyland's aluminum casting expertise was actually superior to GM's. They'd been casting aluminum cylinder heads since the 1940s. They redesigned the block with thicker cylinder walls. They improved the head gasket design. They added better corrosion protection through improved alloy chemistry. The first Rover V8 rolled off the Solihull production line in 1967. It powered the Rover P5B, transforming a stodgy sedan into a genuine performance car. The 3.5-liter version produced 160 horsepower initially, but continuous development saw that rise to over 190 by the 1970s. Then came the masterstroke, the Range Rover, in 1970. The aluminum V8's lightweight was perfect for an off-road vehicle where weight over the front axle destroyed capability. The Range Rover could climb slopes that would leave heavier vehicles stuck. It could ford rivers without nosediving. It became the world's first luxury SUV, creating an entirely new market segment. The engine's development under Rover was remarkable. Displacement grew to 3.9 liters, then 4.2, eventually 4.6 liters. Power outputs reached 300 horsepower in the final versions. TVR used it in their sports cars, extracting 340 horsepower. Morgan, Marcos, MG, they all used variants of the original Buick design. The Rover V8 remained in production until 2006, 42 years after Rover bought the design, 45 years after Buick created it. Over 500,000 were built by Rover alone, far exceeding GM's original production. It powered everything from luxury sedans to military vehicles, from sports cars to ambulances. The technical legacy is even more impressive. The 215 proved that aluminum engines were viable for mass production. Every modern aluminum block engine, from the Ford EcoBoost to the Chevrolet LS series, owes something to the lessons learned from the 215. The permanent mold casting process GM developed is now industry standard. The corrosion protection methods pioneered for the 215 are universal today. Consider the modern context. Today's Chevrolet LT1 V8 uses an aluminum block and heads. It weighs 465 pounds complete, still 140 pounds heavier than the 1961 Buick 215, despite 5 decades of advancement. The 215's power-to-weight ratio of 1 horsepower per 2 pounds was revolutionary then and respectable now. The aftermarket embraced the 215 in ways GM never imagined. Mickey Thompson used disc-stroke 215s in Indy cars, taking advantage of the lightweight for better handling. Repco in Australia developed a 3-liter Formula One engine based on the 215 that won consecutive world championships in 1966 and 1967 with Jack Brabham and Denny Hume. Hot rodders discovered that the 215 would accept surprising amounts of boost. With modern turbos and engine management, 500 horsepower from 215 cubic inches is achievable while maintaining the stock 318-pound weight. That's a better power-to-weight ratio than a modern Hellcat engine. The aluminum technology forced improvements across the industry. Ford developed the 260-289 with thin-wall iron casting to compete on weight. Chrysler experimented with aluminum slant sixes. Even GM's later iron engines incorporated lessons learned from the 215's development. Better gasket technology, improved coolant formulations, precision casting techniques. The financial impact was complex. GM lost money on every 215 built when factoring in development costs. But the technology developed, the casting techniques, the metallurgy knowledge, the manufacturing processes, paid dividends for decades. The LS engine family, GM's most successful V8 ever, is a direct descendant of the aluminum technology pioneered with the 215. Rover, conversely, made the 215 one of the most profitable engines in British automotive history. The tooling GM sold them for $750,000 generated billions in revenue over 4 decades. The Range Rover alone, which wouldn't have existed without the aluminum V8, became one of the most profitable vehicles ever built, with margins exceeding 35%. The human cost of development was significant. 3 test drivers were injured when early prototypes suffered catastrophic failures. An engineer lost 2 fingers when an aluminum casting failed under pressure testing. The Flint factory had 47 injuries in the first year as workers adapted to handling aluminum components. But these sacrifices led to safety protocols that protected thousands of workers in the aluminum age that followed. The cultural impact extends beyond mere transportation. The Rover V8's distinctive sound, a mellow burble completely different from iron V8s, became synonymous with British luxury. The engine note alone could identify a Range Rover approaching from a mile away. It became the soundtrack to British automotive excellence, ironic for an engine designed in Flint, Michigan. Today, surviving Buick 215s are increasingly valuable. Clean examples command $5,000 to $10,000. For just the engine, complete cars with original 215s can exceed $30,000 for pristine examples. The Rover versions are still readily available and cheap, making them popular for engine swaps into classic cars where weight matters. The engineering principles the 215 pioneered are now universal. Variable valve timing? The 215's development program explored it but deemed it too complex for 1960. Direct injection? GM tested it on 215 prototypes. Turbocharging? Oldsmobile did it first on the 215. The engine was a rolling laboratory for technologies that wouldn't become mainstream for decades. Modern manufacturers study the 215 as both inspiration and cautionary tale. It proved that revolutionary technology needs evolutionary introduction. Being too far ahead of the market, the infrastructure, and the service network is as dangerous as being behind. The 215 was right. It was just 20 years too early for American consumers and dealers. The specifications still impress engineers today. The bearing surfaces were held to tolerances of 0.001 inches. The piston-to-cylinder wall clearance was just 0.015 inches when cold, expanding to 0.03 inches at operating temperature. The oil pump delivered 40 psi at just 1,000 RPM, ensuring lubrication during the critical warm-up period when aluminum expands faster than oil warms. The metallurgy was extraordinary for 1961. The aluminum alloy contained precisely 7% silicon, 0.3% magnesium, and trace amounts of copper and zinc. This composition gave the optimal combination of strength, castability, and corrosion resistance. Modern aluminum blocks use remarkably similar alloys. GM got it right the first time. But here's what truly made the 215 special. It proved that American engineers could innovate beyond just making things bigger. In an era when cubic inches were king, Buick created something elegant, sophisticated, and efficient. It was engineering for its own sake, pushing boundaries because they could, not because the market demanded it. The 215 represented a philosophy that Detroit would later forget and then painfully relearn. That less can be more, that lightweight is might, that sophistication sells. Every modern turbocharged four-cylinder making V8 power owes a philosophical debt to the 215. It proved that displacement was just one path to performance. Standing in a museum today, looking at a preserved Buick 215, you're seeing more than just an engine. You're seeing the exact moment when American automotive engineering grew up, when it stopped being about brute force and started being about elegant solutions. That little aluminum V8, all 318 pounds of it, changed everything. It failed in America, succeeded in Britain, and ultimately proved that great engineering transcends borders, brands, and even time itself. The next time you see a modern aluminum engine, and nearly all of them are now, remember that it started with a group of engineers in Flint, Michigan, who dared to build something everyone said was impossible. They created an engine so light that people didn't believe the scales, so smooth that drivers thought it had stalled, so advanced that it took the rest of the world 20 years to catch up. 318 pounds of aluminum that shook the automotive world, not with brute force or massive displacement, but with elegant engineering and revolutionary thinking. The Buick 215 V8 didn't just challenge what people thought was possible, it redefined what an engine could be. And in the end, isn't that what truly revolutionary engineering is all about? Taking the impossible, making it possible, and then watching the world eventually realize you were right all along. What's your take on the 215? Have you ever seen one of these aluminum jewels in person? Drop a comment below and share your thoughts on this piece of revolutionary engineering that was simply too far ahead of its time.